All right, continuing our discussion of work and energy, we're going to add friction into all of this now. We know that to affect the energy of an object that we can do work on it. I alluded to that in the last video. I talked about pushing an object to increase its kinetic energy. I talked about lifting an object and doing work on it in that way to increase its potential energy. We know that work is applying a force over a distance. And we also learned that friction is a force. We know that friction acts on objects that are in motion, and we know that friction acts over a specific distance. We know that it acts parallel to the motion of the object. So we can look at friction exactly like we would look at any other force acting on a moving object. Now, friction, when it does work on an object, what normally happens is that friction is going to cause heat. You know that if you just take your hands and rub them together, because we do that when we're cold in the wintertime. We rub our hands together to try to get them warm because the friction of the motion of our hands, that friction causes heat, causes our hands to warm up. So that particular friction, that force, is going to do work that's going to change the kinetic energy of the object into heat energy. And so again, we've not destroyed any of the kinetic energy of the object. Remember, First Law of Thermodynamics says that you can't create energy, you can't destroy energy. So friction doesn't destroy the kinetic energy. It merely converts it into a different form, and it's going to convert it into heat. It may also be converting some of it into sound energy, because sometimes you can hear when things rub together. So the author specifically mentions heat energy, but there may be some sound energy created there as well. So the key point here is that any work that is done, whether it's the work of a push where you are pushing on something, or whether it's the work of friction, that work goes into the total energy of the system. So we're going to look at example 8.6, and I'm going to analyze this one the same way that I analyzed the roller coaster problem. So if we look at that one, it says a 230-gram toy car is pushed so that it rolls across a level floor. If it starts with a kinetic energy of 0.46 joules, how fast will it be going when it gets to the other side of the room after friction has done 0.30 joules of work? So what have I been given? I know that the mass of the object is 230 grams. Now, anytime I do calculations, if I'm going to be using newtons and joules, I know that mass is going to have to be in kilograms. So I'm going to go ahead and change that to 0.23 kilograms. I'm only going to need two significant figures, so I'm going to take that 0 off of there so that I don't mess those up. Okay, I know that the kinetic energy that it starts with is 0.46 joules. And then I am told that the work due to friction is 0.30 joules. Okay? And what I'm being asked for is the velocity once it gets to the other side of the room. Okay, so let's analyze the total energy of the object. We know that the total energy of the object at the beginning has to be equal to the total, energy at the end. Okay, so the total energy at the beginning, right when it begins moving, is going to be kinetic energy only. So no work's been done on it. It starts out, when we kind of start the camera rolling, we're starting it at the beginning of the motion with kinetic energy only. When I get to the other side of the room, what's the situation on this toy car look like? Well, it still has some kinetic energy, but that kinetic energy is going to be a different amount because we know that the car will have slowed down because of the work that friction's done on it. And so therefore, the work that friction has done is going to take away from what that kinetic energy was. So if I add those two together, that should end up to the kinetic energy at the beginning. So Therefore, the kinetic energy at the beginning was 0.46 joules. The kinetic energy at the end, I don't know yet, and so the work due to friction, I was told, was 0.30 joules. So now simple subtraction will tell me that the kinetic energy at the end is going to be 0.16 joules, okay? Now that I know what the kinetic energy is, I'm going to go up here. I know that kinetic energy is 1/2 times mv squared. The kinetic energy is 0.16 joules. The mass was 0.23 kilograms, and I'm trying to find the velocity. So once I move all these things around and solve for v, my velocity should come out to be 1.2 meters per second, okay? So again, an example here where the examples that we did before, we talked about all kinetic energy and potential energy, but now we're starting to look at the contribution that friction makes to all of this too, and I can add that in with energy just like I did before, because remember, work has units of joules just like energy does, so you can throw that into the same equation, add and subtract them all together.